Now we're going to see the deformed shapes that result from the degrees of freedom that we previously determined. And the main strategy here is to move the node according to the degree of freedom while preventing any other motion from occurring. And we'll see this by example. Again, we'll use the examples A, B, C, and D that we've previously been considering. For example A, degree of freedom 1 was a vertical movement of the right hand node. And we notice that we move that vertically while at the same time prevent that node from rotating. I'm showing that node in the same orientation as before. That determines both the deflection and the slope right at this point. With the deflection and the slope right at this point, we can then come in and join that information with the smooth curve. Degree of freedom 2 was a rotation of the right hand node. Well, I'm showing this node rotated, but I'm not translating it up or down. And so now I determine that translation and that slope. At the left end I have a translation and slope, and I combine that information with the smooth curve. In example B, degree of freedom 1 was a rotation of the center node, and indeed that's what I've done. I've rotated that center node. You'll notice that I haven't rotated, or I haven't allowed that node to rotate, because that's not involved in the degree of freedom. This node, I didn't make this explicitly clear in the previous example, but doesn't rotate, doesn't move because of the fixed end. So now I have this translation and that slope, this translation and that slope, this translation and that slope, and this translation and that slope at each of the 4 locations of interest. I now combine this information with a smooth curve, and I get the deformed shape that I'm looking for. In this same example, degree of freedom 2 was a rotation of the right hand node. So I show that node rotated. However, I do not rotate that node. And now I look at deflections and slopes on the right hand member, right side, left side, on the left hand member, left side, right side, and I combine that information with the smooth curve. In example C, the main difference is that I've chosen not to count a degree of freedom at the free end. So, when I move degree of freedom 1, which is a rotation of this node, I am now allowing that node to move however it is that it needs to move to adjust itself to that motion. The left side of this is exactly the same as in example B, degree of freedom 1, but the right hand side changes. The left side of the member has a 0 deflection and a positive slope, and here I simply have 0 deflection. And so I come in at a natural slope here that allows rotation of the right hand side. In example D, as you'll recall, there was only 1 degree of freedom, and that was rotation of this joint here. But because this is a rigid member, rotation of that joint implies that this other node must move upward, must move slightly to the left, and most importantly, it must rotate as well. At the right side, I have chosen not to count that degree of freedom. I've reduced it out. And so I'm allowing it to rotate however it naturally wants to rotate, given the deflection of the center node. Well, this is a rigid body, and so it just deforms in rigid body translation and rotation. This other node has now a given deflection and a given slope. This node has a given deflection, and we combine that information. Now we have our deflected shapes for examples A, B, C, and D.